So let me for now switch my mode of operation to 1D3Z. And I'm hoping all of these questions I can answer again with 1D3Z, but let me tell you what I have included in this. In the directory 1D3Z, this is the data that we get from BMRB. This is experimental data that have been submitted by people. And in fact, in the case of 1D3Z, more data was used to calculate this structure. I have 1D3Z.4.4. This indicates that I have up to, but not always, up to 4 RDCs per residue from alignment medium 1 and 4 from alignment medium 2. Then I reduce it to 3.3, then I reduce it to 2.2. And I suspect you guys want to see, I don't know which one you want to see, you can pick one. I would assume the less the better. And if you look at my, which one is it? WRDC.1. No, these are the old ones. So this is the data that I have for residue. I have basically, so this one is 3.3. Okay, so I'm going to go to my production. Let me see if I have it there. There's a bit of a mix up here. This is supposed to have only 2 RDCs, but it actually has 3. It works with 2, take my word for it. I don't know why. Okay, so somewhere I screwed up the process of copying data over. But let me go back to the data that you are seeing, you have, and let's just work with 3 sets of RDCs. Let me see what's in 3.3. Maybe I got those. Yeah, so it's 3 sets in here. So let me first tell you what data I have. So we have carbonyl nitrogen, we have NH, and we have C alpha H alpha. Those are the 3 RDCs that we have used from 2 alignment medium for this particular protein. If I was to start Redcraft GUI and switch my workspace to actually here, and so it automatically detects my data and does the analysis. This is a 69 residue protein, some breakdown of what's going on, but this is something you may want to look at. So for example, when we were talking about where would be a good place to start with calculation of structure, you don't want to start from residue 36, 37, for example, because there's just only 1 RDCs per alignment medium. So it would be better to start from a place that there is a higher data density. In this particular instance, it turns out that residue 1 is just a fine place to start. So I'm going to start my calculation from residue 1. I'm going to start with, I'm going to start with residue 1. This one, by the way, I didn't mention anything. During stage 1 of calculation, you can impose a threshold, a cutoff threshold, that all geometries that exhibit the residual dipolar coupling fitness outside of this threshold, you can just exclude out of your analysis. These are all in order to maintain the computational complexity of your algorithm. If you're looking to reduce your execution time, this would be one place. I'm going to reduce this to be ROM level 1, and I'm going to execute stage 1. And so, for example, in stage 1, 1.angles produces list of approximately 182 entries for first one. For the second one, it produces less. And you can see that almost RDC fitness of all the structures are 0. This is because you're actually at this point, you're operating based on an underdetermined system. You just don't have enough residual dipolar couplings in order to decipher the fitness of one geometry versus the other geometry. So at this point, stage 1 performs very little helpful, useful information. Useful information comes when you go to the second stage. And in this particular instance, I have enabled decimation with a cluster sensitivity of 3 angstrom, score threshold of 1 hertz. Decimation applies to the entire thing, and I'm going to cap off the effectiveness of decimation to only contribution of decimation to only 500 new structural clusters. I'm going to minimize my structures using this script, and this particular one I'm just going to erase. There's no point in having that. And I'm just going to start my execution. So execute stage 2. As I monitor what's going on, you can see that at 2.out, I have only 110 structures. At 310, 4 jumps to 142, 137. At 7.out, it jumps to 558. And if you look at this, my data density actually goes down at 7, 8, 9. In fact, I don't have data from the second alignment medium, and then it comes back up at 10 and so on and so forth. So the decimation has a feature that dynamically and adaptively adjusts its depth search to correspond to the degree of data sparseness. So the more sparse data you have, the deeper search it will perform. The more data it has, it will retract to a more shallow search. And then from 9 onward, it becomes less and less. And again, at 12, 13 kind of jumps back up because of whatever is happening with that data set actually at 12 and 13. It is complete data, but the data may not be sensitive, might be erroneous. Somehow the algorithm requires a deeper search. You can—
Home, one sec. So when you showed in that advanced tab, you said 500 clusters in the decimation tab. Can you go there?
So yeah, that is correct. So
500 clusters, not 500 structures, right? Yeah.
There are, let me break it down. So 100 structures, my depth search is 100 structures. So 100 unique structures, specific structures are permitted to go to the next round. That's right. 100 of the 558.
Okay.
10 of those 100 structures will be subjected to minimization. And therefore, the 10 additional structures that you see in all of them, such as, for example, in 2.out, 10 of them are the contribution of the minimization, where the 10 top structures will be selected, minimized, and then inserted back to the list of potential structures. The remainder of it is the contribution of decimation. So in this particular case, 110, 566 minus 110, so that's 450-ish structures.
Right. Yeah.
And the 450 structures are representative of clusters of structures, clusters after this 3 angstrom clustering.
Okay, so like that, 500 clusters you analyze in the outside of this 110 depth, from which you are able to derive 456 best ones.
Yes, but let me refine what you just said. So 500 of them are permitted, the top 500 are permitted, cluster representatives are permitted to go forward. In this particular instance, for 9.out, only 450 were selected to go out.
Okay, I see. Okay.
And in fact, if you tinker with this thing, I'm more than happy to repeat that exercise if time allows. As you tinker with these parameters, this depth searches change.
Okay.
But for now, the search, I believe, is completed or still running. So let's look at some intermediate things. So how successful is my structure calculation at this point? 28.out. In 20.8.out, if I look at my RDC's exhibit, this pattern in general should be that there is monotonically increasing fitness to RDC, which makes sense because you're including more and more RDC as your fragment size grows. And therefore, you are kind of arriving at a true estimate of your error. From that point forward, this dynamic profile should plateau and remain constant unless there is a big jump observed. When you see a big jump, that means something needs to be addressed. So as long as this pattern is observed and your plateauing is as approximately at your expected experimental error level, then your structure is sound and reliable.
Now in the synthetic data, you showed where you showed the last and best profile were converging toward each other. In other words, the is small, right?
Right. So the convergence also indicates an issue. So if you are coming up on what you want to do, you want your search to be very exhaustive as you can, but to include a large number of structures. So if that's not the case, that could possibly indicate problems. So you can see in here,
yeah,
monotonic increasing platform, plateauing, and this marker basically is linearly increasing, indicating a healthy inclusion and evaluation of a healthy number of structures. If they are sort of converging, it's not necessarily a good indicator. So at this point, at residue 52 is a good thing. I can look at the structure to see how well we are doing. Sorry, wrong thing to click on. So 52.pdb. If I go and open the structure of the PDB, this one, and align it, I am 1.7 angstroms away from structure. By the way, so at this point, I must clarify that if your structure is supposed to be beta sheet, don't be surprised if you don't see the beta sheet illustration, because at this point, your structure does not have side chain, and the required hydrogen bonding that may be in place and required by these illustration programs to identify something as a beta sheet may not necessarily be portrayed that way. So for example, in this case, this portion of the protein, the beginning part of it is supposed to be a hairpin beta sheet. It doesn't show up like that only because the side chains are not there, but the backbone RMSD is fairly close. So far, you're 1.757 angstroms away. Let me see how far the structure has gotten. I'm at, okay, so I guess it's completed. So at 69, if I was to open my structure, I am at 1.8 angstrom. The entire structure was calculated in matter of minutes. So in fact, Redcraft tells you at this point, it took 5 minutes, 29 seconds for it to run. And it calculated the structure that it was, it's 1.8 angstroms away from actual structure. This is, again, with ideal geometries. Omega angles are snapped to absolute 180 degrees. All the changes are in rotamer space. So therefore, peptide, bond lengths, bond angles, all that stuff is ideal. However, the algorithm can use a bit of refinement. If you take this, stick it in Explore NIH with the residual dipolar couplings that are used here, if you were to refine it a little bit more, you would find even a closer structure. So my claim from the beginning sort of stands that Redcraft can calculate a high resolution structure, but it can still benefit from a round of minimization, a simple minimization in any of the alternative Explore and IH and things. At this point, I can change my parameters. My search is fairly shallow. My round 2 is kind of shallow. I can play around with these to find even a better structure. But maybe the time would be better spent if I can maybe answer questions and compare and contrast things. Any questions?
So what's the impact of not providing the J?
I'm sorry?
In this, the real data, there are no J coupling values compared to the synthetic ones. You had J also.
Let me see, actually. So let's look. There were no J couplings in this particular data set, and I can confirm it this way, of course. There's no, all the J couplings are 999 indicating
Yeah.
data.
So does it affect your final convergence? I mean, or the RMSD or?
Is purely based on residual dipolar coupling data and no other information.
Okay.
And I'm sorry I don't have that, but I'm almost sure somewhere in here I have a 2, which is we are only using NH and C alpha H alpha are residual dipolar couplings. And in fact, it works better than 3,3.
Okay.
Because the carbonyl nitrogen is really a smaller magnitude collection and it's more erroneous. So when you include that in here, the quality of final structure kind of is reduced a little bit. So if you're interested, I can spend the last few minutes to see if I can find the original 2.2 and we can run that, or we can play around with this a little bit more, or I don't know what, if you guys can, if you want to spend some time doing this on your own. I don't know if Redcraft is working on your servers. So just let me know what's useful at this point. I'm more than happy to comply. Again, we are looking for collaborators. And so structure calculation at this point is somewhat trivial unless you go into structure calculation of more challenging proteins. If you have residual dipolar couplings, we can help you. And of course, our latest interest these days, the buzzword is unstructured proteins, whether dynamical, inherently,
IDBs,
all that stuff. We can help you with that too.
What about nucleic acids like RNA structures?
So the nucleic acids, at one point I looked at it, and unfortunately right now we are not funded to further develop Redcraft. I am seeking funding to change Redcraft in a variety of directions. So if you ever serve as a reviewer, be kind to us. Maybe we can continue this development. But we can also explore in a direction of the nucleic acids. So the principle is very straightforward to translate from proteins to nucleic acids.
Okay.
The only question is how much RDCs can be collected in the world of nucleic acids.
Yeah.
Skeptics at this point, critics of residual dipolar coupling will always, one could sit here from my perspective, I'm more of a computational guy. I don't sit in front of the NMR instrument to collect data, to observe the challenges of collecting data. I suspect the challenges in collection of RDC is the additional alignment media that you need to create.
Right.
I suspect your proteins may not behave well in the aligned samples, but in some circumstances, it may be justified if you just cannot collect the NOEs that you need to fold your proteins. Maybe you should spend a little bit of time, see if you can get a compatible alignment medium.
Yeah.
And then it's the issue of collecting residual dipolar couplings, which from my understanding, you can just really, as long as you have assignment in place,
Yeah,
you can just run some sort of a HSQC to
correct.
your
Yeah.
needed data.
Yeah.